Hello, and welcome to Lecture 4 of Survey 11th edition in this college physics course. Here we're covering a single section, section 2.3. And it may just be one section, but it's jam-packed full of a lot of information to take in. Because it's a big one. It introduces acceleration in one dimension. And there's a lot we can say about acceleration. It's very important. Okay? So we want to relate average acceleration to change in velocity, understand the significance of the special case that is constant acceleration, and its importance. All right? Because really, when we talk about acceleration, most of the time we actually mean constant acceleration. All right? So let's get right into acceleration with the term that was really going to shine later in the book, but is directly related to acceleration, so I might as well define it now. And that's the term of non-inertial reference frame. Okay? So a non-inertial reference frame is simply a location that is accelerating. All right? So if I'm on an accelerating couch, then I'm in a non-inertial reference frame. Okay? Well, a reference frame, because what the heck is that? Is just a technical term that is a location where measurements can be made. Okay? So any place where you make measurements, perform an experiment is a reference frame. Okay? And on the other hand, an inertial reference frame is a location at rest or at constant velocity, which is, in other words, anything that's not accelerating. Okay? So that's the term, just simply related to acceleration. You're not going to see it come up again for a while. What's g? Okay? Well, g is acceleration on the surface of Earth. Okay? Well, okay, great. Gravity creates one acceleration for everything on Earth. We all share the same g. That's why it's kind of special, okay? And that value is 9.8 meters per second squared. These are the units of acceleration. More on that in just a moment. Now, kinematic equations. What are those? Because we introduced kinematics in the previous lecture. So the kinematic equations are equations of position, velocity, and acceleration. You'd think so, but no. The kinematic equations are a set of equations used for solving problems with constant acceleration. The name is misleading because zero acceleration and non-constant acceleration are also kinematic, but any equations related to that type of motion, non-constant acceleration or just no acceleration at all, aren't called the kinematic equations. These very important, they are very important equations because constant acceleration is so common. It's ubiquitous. Okay? All right, well, let's get into it. So here we have some definitions to cover within the formulas, right? Well, just defining the variables. So the first one is average acceleration. This is very similar to the formula you saw for average velocity, but for average velocity, it was change in position over change in time. But of course, v is in position, it's change in velocity, okay? So acceleration is change in velocity per time. That's the definition. Change in velocity per time, okay? The units of acceleration then would be meters per second, which is the meter per second squared. All right. On the other hand, instantaneous acceleration is just the limit where that delta t becomes infinitesimally small. It approaches zero. Okay. I actually had to erase the rest here because I left in the calculus form. But of course, you're not responsible for that. All you need to know is that there's this idea of approaching instantaneous, and you need to know that that is also called the tangent line of a graph, as compared to the secant line, which connects 2 points. Tangent line kisses the curve at a single point. All right, then we just have g. This is up in the key terms, 9.8. One thing I do want to say about it is it's 9.8, but it never limits the number of significant figures. So assume that it has however many significant figures any other value in the problem has. It doesn't have 2, it has however many you need. But it's always exactly 9.8. Okay, so now the kinematic equations. These, okay? So, the first one to look at is displacement for constant acceleration. Okay, that's this one right here. Okay, x equals x naught plus v average times time. Okay, looks good. Okay. Then we're going to look at this equation right here, which is, so kind of jumping up, finding velocity for constant acceleration. Okay, because here we have velocity on the left-hand side. This represents initial velocity, and this is just acceleration times time. So this equation right here should look familiar if you look at it carefully, because it's the equation of a line. Think y equals mx plus b. In this case, b is v naught, and m is a. So that means acceleration, represented by the letter a, lowercase, is the slope. Well, sure enough, the slope is acceleration. This green line is the velocity curve, because this velocity is a function of time. The intercept with the vertical axis, the velocity axis, is the initial velocity, because that's at time equals 0. Okay, all right. Okay, so if we kind of take this formula, the first one I mentioned, displacement for constant acceleration, and we take that notion of average velocity, then we can say that average velocity is just 1/2 the initial velocity plus the final velocity. Well, that actually makes sense that that would be average velocity because for constant acceleration, velocity is linear. So this statement, we can say confidently, is true because velocity is a line. And anytime velocity is a line, the average is just 1/2 the final plus the initial. Okay? All right. Okay? Now, however, most of the time, if you want to find displacement, you're not going to use this formula. You're actually going to use this formula, which is solving for the same thing, displacement, how far you've moved. But notice that it has some different inputs. It still needs the initial position, often 0, but not always. But instead it looks at the initial velocity rather than the average, and it cares about acceleration. So what is this equation? Well, this equation is mathy again. It's just the equation of a polynomial, okay? So it is how you find position for constant acceleration, okay? Because here is position as a function of time, and position is parabolic when acceleration is constant, just as velocity is linear when acceleration is constant. Because all of these only apply to constant acceleration because they are the kinematic equations. Okay? Okay, all right, great. These are going to be some useful formulas. In fact, they're so useful, let's number them. So these are the big three. Well, third one I'm about to get to. Velocity, given initial velocity, acceleration, and time. And position, given initial position, initial velocity, acceleration, and time. All right. So what you can do, though, is you can combine 1 and 2 to get 3. Combining equations 1 and 2 algebraically to get this equation. And you want to do it? Do it. Prove to yourself that you can combine just these two equations, nothing else, and rewrite it as that. And why would you ever do such a thing, other than just some practice with algebra? Well, you can do it because now you've got an equation that allows you to solve for velocity, but unlike equation 1, there's no time in it. You've combined 1 and 2 and eliminated t. Well, that's great sometimes, because sometimes you don't care about time. You're not given it. You don't want to bother solving for it. What if you only care about the final velocity and you're given the acceleration and the displacement? Because this right here is your delta x in the parentheses. Well, there you go. Just bypass time altogether. Okay? So these three equations are the ones you're really going to be using most of the time. Okay? All right. So there's your introduction to equations. Let's get into some practice. Okay, so we have 4 types of problems we're going to see. And I'll define the types, and then we're going to do a concept question to get the ball rolling. But first, the 4 types of questions, okay? So simple problems, type 1, that involve using a single kinematic equation to solve for an unknown quantity like time or distance. So these ones we should be using one of the equations, especially equations 1, 2, or 3, the special ones I numbered, of the kinematic equations, and just kind of plug and chug, solve for something, okay? Done. Type 2 problems require using the kinematic equations multiple times or separately over time periods or distances. So there's a bit more work there. You have to actually do them multiple times. They're a more complex type of problem. Then type 3, increasing in complexity, we now have problems that involve using the kinematic equations for more than one object or particle and comparing the results. Okay, so here's this is a big thing now where we have to actually relate to movements. All right, so there's actually 2 separate moving objects or particles that we have to consider. Okay, so that definitely adds a level because we have to think about how they're moving relative to each other. Often it's simply a matter of setting the position functions equal to each other, but that still requires a conceptual step. And finally, the 4th type are complex problems that involve using the kinematic equations combined with additional conditions and require indirect algebraic techniques. Okay, and I'll show you what I mean by that because I have one example. All right, let's do a concept question. Make sure we kind of understand what we mean by acceleration and a little throwback to the difference between velocity and speed, since change in velocity, after all, is acceleration. So we're looking at 4 graphs of distance versus time. That's what all 4 of A, B, C, and D graphs are. Okay, so these are position versus time graphs. They're all parabolas, okay, so they all represent constant acceleration systems. They might be like, well, they could be a different type of polynomial, but we're going to assume these are all parabolas. So we're going to assume these are all constant accelerations. Okay? Well, let's answer some questions. Okay, so in the slope of the x graph, positive or negative? Is the slope of the x graph positive or negative? And when we refer to the x graph, we're just talking about the distance versus time graph. Okay, so for A, well, first of all, let's look at some tangent lines. All right, so here I just drew two tangent lines, velocity at some point 1, velocity at some point 2. I'm going to do the same thing for each of them. And just remind you, the tangent lines are in green. Okay, these are just the slope at any particular point. Because, of course, the slope changes because, after all, these are curves, not lines. But we can look at slopes at particular moments in time. Okay, and a slope on a distance versus time graph, right? Well, that's rise over run, so that's meters per second. So obviously, the tangent line must be a velocity, hence v. All right, so is the slope of the x graph positive or negative? Well, there's not one value for the slope, but if you look, all of these are sloped up for A, all of them are sloped up for B, all of the slopes are sloped down for C, and so on. So that means we can say that the first two, A and B, are positive, and C and D are negative. Okay? Is the velocity positive or negative? Well, that agrees. Okay? So the instantaneous velocity at any point for position curve A is positive, likewise for B, and at any point it's negative for C and negative for D. All right? So that's all we wrote here. Okay? Now, is the x graph curved up or curved down? Okay. Well, curvature means like a bowl, right? So if it's curved up, then it's like a bowl. If it's curved down, it's like a bowl flipped upside down. So that means A must be up, right? B must be down, and so on. So we see that we got A is up because it's curved up like this. B is curved down, see? C is curved down, you see? And then D is curved up. Okay, you can kind of imagine extending it, right? All right, like a parabola. Okay, so up, down, down, up. Good. Now, it turns out that curvature is acceleration. All right, so if you look at a graph like this, the curvature represents the sign of acceleration. Okay, sign of acceleration. So anytime you have positive curvature, you have positive acceleration. So that would be like A. Anytime you have negative curvature, downward curvature, you have negative acceleration. Interesting, right? Okay. Okay. Now what about velocity? Is it increasing or decreasing? Well, the first one we can clearly see it's increasing, right? It's getting steeper. All right. What about B? Well, B is decreasing, right? It's getting less steep. So you might be like, well, C is also increasing, right? It's getting steeper, but it's getting more negative, and velocity is a vector, not a scalar. So I mean, think about it. If this velocity right here is, say, negative 1 meter per second, maybe V2 is negative 3 meters per second. Well, what's the smaller number? Is negative 3 smaller than negative 1? Of course it is. So C is decreasing. Likewise, D is increasing, because here, maybe negative 3 meters per second, and over here, negative 1 meter per second. Well, negative 1 is larger than negative 3, so that it actually increased in D, increasing. Okay? But speed is just the absolute value of velocity. It is a scalar, so it doesn't care about the sign. It only cares about the actual magnitude. So increasing because there's actually a larger value, right? Decreasing because the value is larger. And then here, C, the first disagreement, here the speed is increasing, okay? Because a larger negative velocity is, after all, still a larger number, and so the speed is increasing. So this is a great kind of throwback, a great reminder of the difference between speed and velocity. And the whole concept question applies to all of kinematics. Right? A nice summary of how acceleration relates to both velocity and speed, as well as position graphs, as shown. All right, let's move on. Okay, so let's look at a simple example. We're just going to use one kinematic equation. A car traveling at 30 meters per second screeches to a halt, leaving a 55-meter long skid mark. What was the car's constant acceleration while braking? All right, let's take a look. So these are known quantities. Sometimes it's a good idea, especially when you're first getting practice with these problems, to write out everything that you know. That way you can find out your missing variables. So we know the initial velocity, we know the initial position, we know the final position, and we know the final velocity. Okay, so really we just don't know the acceleration. Okay, so we're going to use this equation here, kinematic equation number 3, as I called it, and we're just going to solve for A. All right, so I just plug in my zeros where they are. Move some things around, isolate A, make sure to divide by 2 times 55, because that's the coefficient on A. All right, I include all my units here. You can see the units are going to work out, because my numerator is going to have meters squared per second squared, and I'm going to divide by meter, so I'm going to be left with just a meter per second squared. And it looks like it's going to be negative. Sure enough, negative 8.2 meters per second squared. 2 sig figs, because that's what I was working with. And it's negative because it's braking. It's opposing the initial velocity. Okay? It's in the opposite direction. So if we call left positive, then the braking would be to the right. Okay? All right. Hopefully simple example. Let's move on to another one. Okay? All right. So in this one, we have a bicyclist starts from rest and accelerates at 4 meters per second for 3 seconds. Then the cyclist travels a subsequent 20 seconds at constant speed. And then we want to know the total distance the cyclist travels. All right, so this is a type 2 problem because there's 2 segments of motion. There's a constant velocity segment and then a following constant or initial constant acceleration movement followed by a constant velocity movement. Okay, so we got to kind of consider the 2 sections of movement because there's different equations to pertain to both of them. So I would say the total displacement, x sub tot, so x total, equals the displacement while accelerating plus the displacement while maintaining constant velocity. I've color-coded them as kind of pink and turquoise here, or teal or something. All right, so then I have total displacement. And here I just have equation 2 of the kinematic equations because that has everything I need. It's got initial velocity, okay? It's got acceleration, okay? Good. And it's got initial position. These are all things I know about the system, okay? And then I've got my constant velocity movement, which doesn't have an a in it at all because a is 0 after all when you have constant velocity. There's no acceleration if you're maintaining constant velocity. There's a v final there. We're going to have to find that, okay? And then times the t2, because there's 2 separate times, right? t1 is 3 seconds and t2 is 20 seconds. Well, what about v final? Well, we need v final. And to find v final, we're going to use a kinematic equation 1. Because again, we have everything we need. Initial velocity, acceleration, and time 1. And you might be like, really? We have initial velocity? Well, yeah. We were told it started from rest. Oh, that means it's v naught is 0, right? But what about initial position? Well, we weren't told an initial position. But we were asked for the total distance it goes. Well, so then we might as well just consider the starting location 0. There's really no reason not to. Okay. All right, so let's move on. So first of all, let's find v final. So v final then is just 4 times 3, again because v naught is just 0. All right, 4 because we were told it's accelerating at a rate of 4 meters per second squared, and it did it for 3 seconds. So that means after the acceleration portion of its movement, it reaches a velocity of 12 meters per second. And that's its final velocity because then it maintains that 12 meters per second for 20 more seconds. All right, so now we're going to plug everything in. 0 for initial position, 0 for initial velocity. 0 times time is just 0. 1/2 because the equation has a 1/2 in it. The acceleration during the first 3 seconds. The first 3 seconds, make sure to square it. And then plus 12 times 20 because this is the whole constant velocity bit of the movement. Do the calculation. We find that the bicyclist covers only 18 meters while accelerating, but once they reach that final speed, they coast for another 240 meters because, of course, it's a much longer time. And then their final displacement is 258, but we only had 2 sig figs, so it rounds to 260. All right? Okay, so let's move on. Okay, so now example 4. Okay, another problem that involves 2 segments of motion. Okay, and this is kind of almost a subcategory of type 2 problems because it's the one where you have idea of an object that's going to decelerate to maybe avoid something, usually a car, in this case a car trying to avoid hitting a deer, but there's this idea of reaction time because it's very real life because it's true. If you do need to brake in an emergency situation, you can't do it right away. It takes a few moments or a second or a fraction of a second to actually start to brake. And that figures into how far you go before you finally come to a stop. Okay? So you're driving your car at 12 meters per second when a deer jumps in front of your car. What is the shortest stopping distance for your car if your reaction time is 0.8 of a second and your car brakes at a rate of 6 meters per second squared? Okay? So pretty big braking acceleration. This is you almost being twice as heavy, right? So it's pretty significant braking. But let's see. Let's see your minimum stopping distance. Okay. So the idea, your x min, is going to be your initial position plus your initial velocity times time minus 1/2 times the acceleration times t squared. So why the minus, right? Well, because we're trying to have a negative acceleration. We're trying to find out how far you're going while braking. Okay? Here's a picture. Here's the car with its initial velocity of 12 meters per second. Here's the distance you're trying to solve for, x min. And you know your final velocity must be 0. Okay? Your final velocity must be 0. Now, I'm assuming that final velocity is occurring somewhere near the deer. This is my wonderfully drawn deer. Okay? So, x naught is the distance covered during reaction time. Okay? So x naught here is not to be 0. Because the idea is that this x min represents the distance covered while braking, okay? But there's some time that you moved before you even began braking, okay? So then we see then that x naught is v naught times reaction time. We know v naught is 12, we know reaction time is 0.8 seconds, so that means you covered 9.6 meters, almost 30 feet, actually slightly more than 30 feet, before you even push your foot on the brake, okay? All right, so now we find the time t brake is found from this equation here, because we don't know t, right? We're trying to solve for x min, but we can't solve an equation of two unknowns. But we can find t from kinematic equation 1. See how we have to kind of fit the kinematic equations together? Think about what are our unknowns, how do we find them, right? Well, we have everything we need from equation 1 to find t, because we know initial velocity, and we know final velocity, and we know acceleration. We just don't know the time to brake, okay? So final velocity is 0, because you're coming to a stop after all. Initial velocity, a sub b for brake, and t, okay? So now I go ahead and solve for t, all right? It just ends up being 12 over 6, or 2 seconds, okay? So then the total braking time is 2 seconds, okay? So now we put it all together. We then find our minimum braking distance, 9.6 meters, okay, plus the 12 times 2 seconds, all right, and then minus 1/2 6 times 2 seconds squared. And again, hopefully this minus makes sense, because this is still going to give us a positive distance. The reason it's minus is because the acceleration is in opposite direction of the initial velocity. And we have to stick with a coordinate system. If I'm calling this the positive x direction, then acceleration points this way. Thus, acceleration is negative. It's a vector, okay? So you have to have the negative there. Otherwise, you'd be greatly overestimating the braking distance, okay? So then we can plug in all our times, or plug in all our values, the time we solved for, the initial position we solved for, and we get 21.6 meters, okay? Which is pretty darn far. I mean, we're talking like, 70 feet. But this also isn't the best reaction time. 0.8 is pretty slow. Okay? So hopefully that is a good problem. Makes sense. A little bit more complex. Okay? So now let's look at another type of problem. This is a type of problem that involves two objects. You might be like, well, didn't the last one involve two objects because there was a deer? But the deer wasn't moving, so it wasn't figured in. Now we have two moving objects, a student and a bus. Okay, so let's read the problem. A college student is running as fast as she can at v max equals 5 meters per second in order to catch a bus. At the same moment that the student has achieved and maintains that running velocity, the bus is 40 meters in front of her. Okay? So that's when we're starting our clock. That's when we start paying attention to the system. It's like we just noticed, like, whoa, wow, she's running after that bus. Okay? The bus is in front of her, pretty significant distance, but we can see she's gaining on it because the bus, at that moment that it's 40 meters in front of her, starts to move from rest. Okay? So essentially, she saw it at the stop, and it's starting to take off, but she still thinks she can make it. Okay, so she's going to chase after it. All right, so that bus, however, is going to accelerate. After all, it is starting from rest, and it's not to remain at rest, so it's going to accelerate. And it's going to accelerate the whole time. We're not going to have the bus like accelerate and then start to coast. For our purposes, the bus is just going to continue to accelerate. Okay, and it's going to accelerate at a pretty gradual rate, so slow rate of 0.17 meters per second squared. Okay, all right, so question A. How far and for how long will the student have to run at that maintained maximum velocity of 5 meters per second in order to overtake the bus? Okay? So I'm assuming she's going to catch it, and indeed she does. Okay? So let's look at the approach here. So to find when the bus and student meet, we set the two time-dependent position functions equal to each other and solve for t. So what we're doing is we're setting kinematic equation 2 equal to kinematic equation 2. So so it's just 2 for the student equals 2 for the bus. And this is just the 2 being the one that I labeled 2 on the page with the formulas. Okay? So what does that look like? Well, that's just x bus equals x student. We expand those terms out because we're actually going to use the full form of the formula. Okay, so for the student, we've got an initial, or excuse me, for the bus, we've got an initial position of 40 meters. I put the units in there. And then we don't have a V naught because so the V naught T just equals 0 because the bus started from rest. So notice there's not a second term. So we just go to the third term, the 1/2 AT squared term. And there's 1/2, there's the acceleration of the bus, which is positive, and T squared. Okay. Meanwhile, we have the student. Okay. Well, the student doesn't have many terms. The student does not, X naught for the student is 0, and A for the student is 0. Okay, so the only term for the student is just velocity times time. It's just the middle term, V naught times T. Okay, so that means we look at this equation. There's only one unknown. That's a relief. So we can just solve for T. Okay, great. So solve for T. But the thing is that we've got a T and a T squared. So you either use a calculator and solve it, maybe by graphing it and finding the roots. You use a polynomial solver, which are built in scientific calculators or plenty of programs. Or you use the trusted quadratic formula, the old negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so that's what I do because I think it illustrates the idea well. So we look here, and we've got, because I'm just solving for t, my variable, I've got my negative b, right? And my negative b becomes positive 5 because we have to imagine putting all of the terms over on one side. And if I move this term over, it's going to pick up a negative. Plus or minus b squared, anything squared is positive. That's why I don't bother putting the sign over here, right? And then minus 4ac, all over 2a. And 2a, after all, is just going to be 2 times 1/2 times 0.17, which is why it's just 0.17, because the 2 and the 1/2 cancel. Okay, so quadratic formula. We can simplify this a bit. I'll leave off the units to make it a little bit easier to read. And I know the final answer is going to be in seconds, so I just kind of fake it and put the units over there. Okay? And what does that give me then? Well, it's going to give me two solutions, and the smaller solution is 9.55, okay? And it's time, so 9.55 seconds. Okay, so what's that telling me? Well, that tells me that that's a point where the student and the bus are at the same position at the same moment in time. Okay? Well, if that's the smaller of the two solutions, that must be when the student first catches the bus. Okay? Okay, that's our answer. Okay? This time represents the moment the student passes the bus. Okay? Now, in real life, they might not continue to pass the bus. They might be like, hey, I made it, and jump on or something, or bang on the door. But we'll continue. And let's find out how far the student had to run. Because at that point, that's pretty easy. After we found the time with the quadratic equation, by setting the two position functions equal to each other, well, now we can say, okay, well, we'll just plug that back into either position function. The much easier one to do is the student's, but you could use either. They will agree. So you just take 5 meters per second, the maintained velocity of the student, times the running time, multiplied by the running time, and we get 47.8 meters. That was a pretty good run, okay? But she made it. Now, in part B, I asked, the solution above has a second solution. The quadratic equation does here. And the second solution is positive, so that means it probably means something. So what is the significance of that solution? And I say that it's positive and that's important because if it's a negative solution and it's time, you can throw it out because that makes no physical sense. But since it's a positive solution, it does make physical sense. What's it telling us? Well, let's look. So the larger second solution to the quadratic formula is 49.3 seconds. Okay? And this is the moment, okay, the bus passes the student. Because that's the idea that the student would just continue to run for some inexplicable reason. And eventually, though, the bus will, since it's accelerating, get faster and faster and faster, and eventually overtake the student. Okay. So then at this moment, the velocity of the bus would be, because now we can just plug it in using the time, would be, so initial velocity of the bus is 0 since it did start from rest. It still maintained that acceleration for 49.3 seconds, a while, and it got up to 8.38 meters per second. Okay? It's like 30 miles per hour. All right? So, yeah, that probably didn't happen, right? But it still is physically possible. Okay? And essentially the idea is that you have some linear function, and then you've got a polynomial that will look like that. So there's two intercepts between those graphs. Okay? Graph it for yourself. Highly recommend it. Okay? All right, let's look at the last and most complicated type of problem. So if you look at it, it almost looks identical to the last one, okay? But this is one where I claim that there's a more subtle method of solving the problem. These are the problems, these are the tricky ones. These are the ones that are on the level of the weekly challenge problems, okay? But I include some of those in the lecture notes as well, So a college student is running as fast as they can at Vmax, okay, 5 meters per second in order to catch a bus. At the same moment that the student has achieved Vmax, the bus is 40 meters in front of the student and starts to move from rest, okay? That's all the same. The bus moves with constant acceleration of 0.17 meters per second. Here's something different. If the running student experiences a negative acceleration due to fatigue, then what is the largest value of acceleration possible so that she still catches the bus? This fatigue acceleration begins the same moment that the bus begins accelerating, okay? Oh, that's interesting. It's kind of more real life, right? So instead of her maintaining that perfect velocity of 5 meters per second for the entire, what was the time for her to catch it, the entire 9.55 seconds, now we're going to say, no, she is slowing down, but we still want her to just barely make it, okay? Well, initially, it's the same idea. For the student to catch the bus, the two position functions must equate. So we're still just going to set x bus equal to x student. The only difference is that the position function for the student is going to be slightly different. It's just going to have another term now. Let's see what that looks like. Okay, so on the left-hand side, it's unchanged, right? Still x naught and 1/2 at squared for the bus. On the right-hand side, we still have the v naught t for the student, but now we have a 1/2 at squared student or equation for the student as well. Okay, notice it's negative because the acceleration would oppose in direction the velocity of both the student and the bus. Okay, it's the only thing pointing, say, to the left if both the velocities are to the right, and as well as the acceleration of the bus is to the right. Okay? Okay. So, how do we solve this problem? Because, a couple examples ago, we had an equation that had more than one unknown, and I said, oh, well, we just got to use another kinematic equation and then work it out to find the other unknown. But we can't do that here. There is no other missing kinematic equation. So, here comes the subtle part. The way to solve this problem, okay, is not with the single equation, because there's two unknowns, but instead we evaluate the radicand for a single real solution. Okay? And you could kind of take a graphical approach if you really kind of want to think about it. But mathematically, there must be only one real solution. Because if we set up the quadratic formula, the expression inside the square root, which is called the radicand, it's the term for it, has to be greater than 0. Otherwise, there's no real solution. And imaginary solutions, the mathematical idea of imaginary solutions, like lowercase I, have no physical significance. You'll never see them in a physics class. So, okay, so that means that is an extra restraint on the system, which allows it to be solvable. Let's see how. Okay, so we look then. We're going to just rewrite everything on one side. All I've done is just move both the terms on the right-hand side of the equation to the left-hand side of the equation, okay? And I combine the two like terms that had a t squared attached to them. Okay, that's where you get this, okay? And why is it plus a? Well, it's plus a because I moved it, okay? The same reason it's minus 5t, okay? Now I'm just going to do the quadratic equation, plug everything in. That's all I've done here, okay? But now check it out. I'm just going to look at the radicand. I'm going to ignore everything that's outside of the square root because that's not going to affect the solution that was asked to find. Okay? The radicand must be greater than 0 for a real solution. Okay. Well, if I look inside, there's only one unknown inside that square root. And I then can set that as an inequality greater than 0. But actually, I don't even need the inequality. I can just set it up as an equality. I can just set the radicand equal to 0 because I'm looking for max fatigue. Well, the biggest acceleration that would work, the maximum fatigue acceleration, would be the point right at which the square root is equal to 0. Just at the tipping point until it becomes undefined or imaginary, depending on the mode of your calculator, right? So that's it. I don't have an equation, and I can just solve for A. I'm going to go ahead and do that. Couple steps here, clean some things up. All right, I just divide both sides by 5 meters per second squared. All right, actually, I just move it over. I haven't divided. I just move it over, and 5 just becomes 25. Okay, then I'm just starting to isolate my A. At this point, I divide both sides by 80, which is where the 0.313 comes from. All right, and then solve for A, and here I'm just identifying it with the subscript that it is, after all, the fatigue acceleration, and I get 0.143. Well, that's pretty neat, because that's actually just a little bit slower than the positive acceleration of the bus, right, which was 0.17. Okay. Now, it will take longer. If we were to plug that back in and find out how much time it takes, we'd find the point that it's no longer 9.55 seconds, but she would just make it, all right? There'd be a single point. And the graph in this case will look something like this. Here would be the acceleration of the bus, here would be the acceleration of the student, and negative acceleration, and they would just touch at one point right there. Okay? Again, graph it. All right, so this is the last example. Obviously, there's more for practice. It's a lot to take in, but we're really getting to a big, crunchy part of the course. I often find that these kinematic equations are confusing at first, but then become so just ingrained in the problem-solving process of this course. So if you feel a little overwhelmed, I've seen it so many times that these ideas will sink in, and they'll seem downright easy compared to stuff that we'll see in future chapters. Okay, so take the time with them, accept that it is a little bit of upfront stress, but you'll get used to them. And thank you so much for watching this video, and look out for lecture 3 later this week. Well, the third lecture of the week. The third lecture of this module. You get it. All right, thank you for watching.